Bienvenido a un nuevo evento de Cátedra Europa.
Good afternoon, good morning. On the behalf of the 24th edition of Cátedra Europa, we give you a very warm welcome to the lecture, Algebra and its Connections, for which we have the special participation of Dr. Ana Ross Camacho, Profesora Investigadora, University of Cardiff, Dr. Andrew Baker, Honorary Senior Research Fellow in Mathematics at University of Glasgow, and Dr. David Towers, Professor Researcher in the University of Lancaster. We will now leave you with Professor Adriana Mejia, who will be moderating the session. Welcome, everyone.
Good morning, good afternoon, everyone. For me, it's a pleasure to present to the first speaker, Professor Ana Ross Camacho. She is a researcher in mathematics, focuses on categories and connection with physics. She is one of my female collaborators, so it's a great pleasure to have she in this talk. Ana.
Thank you very much for the invitation. Thanks for having me here today. It's my great pleasure. Colombia, terra querida. I would have loved to be there. Hopefully next time. So as Adriana was saying, today I'm going to talk to you. I hope everybody, can everybody see my screen? Hopefully it's seeable. I would like to tell you today about algebra and mathematical physics. I mean, what kind of connections can we make? I have pitched it at a very basic level, so to make sure that everybody is on the same page. So, hey, but first let me introduce a little bit myself. As they said, I'm Dr. Ana Ross Camacho, but please call me Ana. Lecturer at Cardiff University. I'm still on the probation, and I was very lucky to start in January 2020. Right before the pandemic hit. I'm a member of the Geometry, Algebra, Topology, and Physics group. It's a very nice multidisciplinary group we have in here that cares about geometric, algebraic, topological aspects of physics. And I mean, I confess, I have a background in theoretical physics, but right now I work in quantum algebra among some other people with Diana. I mean, and in particular, work on algebraic aspects of mathematical physics. If you ever want to come to Cardiff, please do it. It's a very lovely city. It's the capital city of Wales. And there's like many lamps, many castles, very green and lovely people, I have to say, including Maridoman. So my plan for today, it's to start with a little intro into algebra. I would like to give you just a taste of what categories are in a nutshell, and also this, and then going to mentioning some of the connections this has with mathematical physics. So let me start with a little bit of history. Well, algebra, which comes from the Arabic algebra, I mean, it can be translated as a reunion of broken parts or bone setting. Actually, I was very amused at this translation. Bone setting is like really pushing some bone back to the place. This comes from one of the basic treatises in algebra. From which page is taken from by Al-Khwarizmi. This comes from the title of this book called The Compilation of Algebra and Other Techniques. But let me just don't get ahead of myself. By algebra, I mean the branch of mathematics that studies some mathematical symbols and the rules you have to manipulate them up and down. It can be as simple as a sum, as we know from numbers, but it can be something more complicated. And not only these rules, we will also like to study the symmetries. This branch of mathematics started roughly in ancient Babylon, about 2000 before Christ, and it was mostly arithmetic. It was mostly like, doing some calculations, easy equations to solve. Kind of very applied problems into real life. Then jumping into ancient Greece, the Fontes and Hera of Alexandria, they introduced some geometric methods into solving some of these equations up and down. And then I can remark two more, let's say, milestones in this story. One is in India with Brahmagupta, which work a lot on arithmetic aspects, again, of algebra. And these very important mathematician, Al-Khwarizmi, which lived in Persia and, let's say, settled, I mean, there's some discussion, academic discussion on this, but he settled algebra as a discipline by itself. This is like the two competing godfathers of algebra, Al-Khwarizmi and Diophantus. And this is like 2 pages of their most important works. So great. Once we, what kind of structures do you encounter in algebra? I mean, at the beginning, it was something, let's say that, but by now I would say pretty simple. Numbers, could be natural numbers, could be rational, complex numbers. I was a bit, maybe not too far away, too distant in the past. Polynomials, as I mentioned, algebra started as some kind of arithmetic discipline, trying to solve some basic equations and some and also vectors, matrices. I mean, nowadays we have like much more sophisticated structures, much more abstract structures, and we have concepts like fields, like groups, algebras, rings, and everything pimped up. I mean, with many adjectives, depending on the properties they may have or not. So just to give you a flavor of this, how these structures work, I mean, for some of you that don't know, some basic example is the one of the definition of group. But what I mean by this is a set, I'm going to call it G, together with a sorting operation. Let's just put it like a dot. And I mean, this operation, you can think of it like a sum, a multiplication, things like this. And I want this operation to have 4 properties. The first one, closeness. I mean, that means that if I have 2 elements in my set, G and H, and I multiply them with this operation in here, whatever I get needs to be still in that. So for example, if I'm trading, integers, if I have one integer 2 and I have another integer 3, I add them. So 2 plus 3, then it will be 5 with, again, an integer. So this is what I mean by closeness. Associativity means that, if I have 3 elements in my set G, let's call it GHJ, then if I compose the first 2 with this operation, and then the third one, it should be the same as if you compose the last 2 and then the first one. So it's like, it really doesn't matter where you put these brackets in here. 2 more things. Well, I mean, there should be some kind of boring element. So some element that whenever you apply the operation to, really doesn't change anything. So some E in my set, such that for any other element I have in my set, then if I multiply with, this G, with E on the left or on the right, it really doesn't change. I'm just going to go back to PG. And inverses, I mean, for every element I have in my set G, there should be another element also in my set, such that if I compose these 2 together, I mean, with G minus 1 in one either way, so it doesn't matter which order, then you get back this boring element, the identity element. So, as I mentioned, one of the basic examples of groups appeared, that appear in the beginning of algebra, although they really didn't know if they were talking about groups. So were, for example, the numerical cases, easiest one, as I said, integers with addition. So closeness means what I said, if you have 2 integers, you should get back an integer. Associativity, we all know that actually, for addition, it will work. So if we sum 2 plus 3 plus 5, this should be the same as summing 2 to 3 plus 5. The identity element in this case will be 0, because if you sum it to any other number, nothing is going to change. And inverses are given by negative numbers. So if you have some number 2 plus minus 2, the inverse, then you should get 0 back, which is your identity element. These are really numerical examples. They're like by far the easiest. But there's something more sophisticated. One can define some groups in terms of polynomials with Galois groups. One can also define groups in terms of matrices satisfying certain conditions, like this one GeoGeoR. I mean, this is a little bit of part of the, of history of mathematics. I mean, these two titans here, Évariste Galois and Sophus Lee, who are really, really important figures in the story of groups. And I have a question for the audience. I mean, given this definition, will anybody like to tell me if a WhatsApp group is actually a proper group as we're defining here? Any ideas? Just pop it on the chat. It would be great if you come to any. But let me not stop here, because I mean, actually, with groups, this is a very interesting structure. But the thing is, what if I want something more? So, like, what if I don't want to just focus on groups? I just want to get like all of the groups I can think of. So, is there? My question here is like, is there any algebraic structure that we can gather where we can gather, like, for example, all the groups that we can think of, or all the fields I can think of, or all the vector spaces I can think of? So one algebraic structure where I can collect everybody in, one algebraic structure to find them, to bring them all together and put them under our understanding. And a little bit beyond this, if I have, suppose, this collection of groups, and then have some other collection of sets, like, can I relate these notions in some way? So like this algebraic structure controlling them both, can I compare them in some way? Can I match properties from one side to the other? For example, groups in particular, they are sets. It's just that we have this extra operation. So how can we, if we have this exotic algebraic structure, how can we compare this collection of groups to this collection of sets altogether? In a little bit of, sorry, I really couldn't hold my geek myself. If we have the 3 rings for the 11 kings, how do we compare them to the 7 rings for the 12 laws? The answer to this question is categories. And I could really put it, I can just ramble on how wonderful this tool is, but there's somebody who said it better and said it earlier than me, which is this wonderful mathematician, Emily Real from the Johns Hopkins University. And in her glorious book, because it's a very lovely book, Category Theory in Context, in the preface, she says, quote, "A category is a context for the study of a particular class of mathematical objects. But," I'm skipping here something, "classifying these objects, this is not the main point. Rather, the action of packaging each variety of objects into a category shifts one's perspective from the particularities of each mathematical subdiscipline to see potential commonalities between them." So it's a marvelous, not only because it's great to have all the possible, for example, groups in one place, it's also because you just have, look at with perspective to not only groups, but any other structure want to relate it. And using these potential commonalities, you can see relations between these different, possibly very different mathematical entities as it happens in mathematical physics. I'm going to go into more detail later. So this is actually the perfect tool we want to use in mathematical physics. So off we go. I would like to introduce you to them in a nutshell. Really going into details. Please do not hesitate to ask if you have any question. Categories were first introduced by Allenberg and McLean in around 1945, and since then they have blossomed all together. Roughly speaking, I really don't want to go into very technical details, but a category consists of a collection of objects, X, Y, Z. It can be actually groups. It can be actually a set. And a collection of arrows between any two such, F, G, I'm going to note them by F, J, G, and H, sometimes also called morphisms. And I will also need a way to compose these arrows. So if I have some arrow from X to Y and Y to Z and Z to W, I can actually go from 1 to here to here. Oh, and Another thing I'm going to ask for the arrows is that I'm requesting that for every object I have in my category, I'm going to need an identity object. An identity morphism that just goes from this object to itself. And what I'm going to ask about this is that, these collection of objects and collection of morphisms satisfy properties like, similarly to the case of groups, if we compose first these two arrows and then the third one, then this should be the same as if we compose these two first and then the first one together. So it's some kind of associativity in a sense. That's for the composition of arrows. And then I also will request concerning these identity morphisms that if I first compose these identity morphism, and then if I compose this identity morphism with an arrow, then it should give me the same as if I take the arrow and then compose with identity on the target object. I'm putting a little star in here since there are some sub-theoretical things to take into account whenever you define this collection of objects. It's not exactly harmless. You have to take classes. If you take sets, okay. Just be careful you don't jump into Russell's paradox, which, by the way, he was born and died in Wales. Some examples of categories are, for example, easiest thing, the sets. Your objects are going to be sets, and your morphisms are going to be functions between, total functions between any two sets. Something more slightly more sophisticated, vector spaces. So your objects, they're going to be k vector spaces. I'm not limiting for now into finite dimensional or not. And your morphisms are just linear transformation between any two vector spaces you can define. For groups, as I said, again, we have objects, groups. And morphisms, a group homomorphism between any two groups. But these three first cases, they are really, they're, let's say, more algebraic. Actually, you can define many kinds of categories. And for example, if you want to go somewhere beyond any algebraic structures, you can also define things like this category cup is going to be relevant for us later, where the objects, they are going to be one-dimensional manifolds with, compact, without boundary. If you don't know exactly what a manifold is, just think of a big surface behaving very well. And if you can link them, link any two of these surfaces with, some other to them, one-dimensional higher manifold, then this is what you will have in your category. So, really, what we're doing with categories, it's not exactly like skipping away. If you specialize enough, then you should recover all kind of the usual notions you should have in group theory, even in your linear algebra class. So, one thing, one notion we can mimic is, for example, that of isomorphism. So if you have two objects in your category and some arrow, let's call it F, between them, I'm going to call F to be an isomorphism. If this F goes from here to here, well, some arrow here to here, satisfying that if you compose it in other ways, so first F and then G should be identity, and the same that if you take the second and then the first one. So if you compose this way, then you should get the same as if you compose this way. Similarly to your linear algebra class, I'm going to denote it like with this wheel in here. And just let me give you two for vector spaces. This is the usual notion. You recover the usual notion of isomorphism of vector space. And if you have groups, well, here you have what you have in here is a bijective group homomorphism. Great. So we have introduced the notion of a category. Then how can we jump from one to the other? So remember the example of the rings. How do we go from one, if we have two categories, how do we go from one place to the other without losing all this structure? This is what it's called a functor. If you give me two categories, C and D, this functor here consists of, a functor consists of, for every object you can have in your source category, an object, you should have an object which is its image into D. And for every arrow you have in your source category, you should have another arrow in the target category. And of course, since you want to preserve all the structure you're given in the original category into the, and I still have something in this target category, sorry. So of course you need this F to preserve composition of morphisms. So if you have some composition of two morphisms G and F, they should be mapped into what you expect. So if X should be mapped to F of X, Y to F of Y, and Z to F of Z, then this morphism here should be mapped to F of F, G to F of G, and that's it. Similarly, you also want to preserve not only composition of these arrows in your category, but also the identity, these identity morphisms we have. So if you apply a functor, you have the identity morphism of X into itself, then you should get the same as if you take the identity morphism of the image under the functor of your object. And this will be identity of F of X. Easy examples of identity functors is of identity functors. Of a functor is, one is the identity functor. So just take every object in your source category to be the same as in your target category. But for example, something that I kind of suggested before is the notion of a forgetful functor. In this case, you can think of it whenever you simply take the structure of the group, the category of groups, and then forget about the operations, and then you will map yourself into sets, the category of sets. But actually, the notion of forgetful functor is used all around whenever you're just forgetting some structure in whatever category you use. So one more tiny detail. How do we relate functors together? So if you have two ways of jumping between two categories, how do you match them together? I promise I'm going to stop being so technical in a second. So if we have two categories and two functors between them, I'm going to define the notion of a natural transformation consisting of a collection of arrows, so that if we have two objects and a morphism in my category, apply the functor to the one side, and you will get F of X, F of Y, and F of F. Apply the second functor, G, you will get G of X, G of Y, and G of F. And then your natural transformation is going to guarantee that it's going to give you a way to go from this, let's say, the image of this functor into the image of this other functor via this collection of arrows. So if every of these natural transformations are actually isomorphisms, this is what it's called a natural isomorphism. And why am I mentioning this is because this notion allows us to compare categories. We can establish that two categories are equivalent if there exist functors, as was going from one category to the other, and the reverse way, D to C. And natural isomorphisms satisfying it. If you compose them in either way, then you're just going to have the identity functor. So, this is great. This actually gives us the notion of equivalence between categories. And this is actually something we want in mathematical physics, because saying that two categories are equivalent allows you to start searching kind of similarities between between two different, possibly very different structures. By the way, concerning this internal structure, there's plenty of structures one can define inside the categories. So there's a notion of direct sums, tensor products, duos. It's a bit, if you think of vector spaces, it's like, trying to get everything you want from linear algebra, but I'm going to skip it for the sake of time today. And one last definition is that, not only once we have a category, we also want to mimic, inside this category, we want to mimic some kind of usual notions. Kind of objects that have some special structure, that we can reduce to if we choose our categories wisely. This is a little bit the idea behind what is called categorification. And suppose one example of this is the notion of an algebra. So if you have some category that has a well-defined notion of tensor product, I'm skipping completely what this means, but just if you think of vector spaces, just think that you have some tensor product between objects and everything behaves well, and this will be just some kind of identity object. Your object A is going to be called an algebra if it comes equipped with two morphisms, so some multiplication map that goes from two copies of your object into itself. Whoops, why I can't see an arrow? Okay, this should, and some unit maps that goes from the product of this unit to the algebra into itself. And then you want these maps to have some associativity and unitarity properties. So when what did I mean with categorification is like, it's actually what happens in the case of vector spaces. You reduce yourself into the case of finite dimensional vector spaces. This notion of algebra reduces to the usual notion of K-algebra. So it's like exactly what we want, like having some notion that recreates the notion, some well-known notion, but like more general setting. So not only we can find, there's more algebras, two algebras, sort of saying. All right, so while we're here, we have all the mathematical ammunition loaded up. So now let's go into mathematical physics. I'm including here some personal definition of what this means. There's not a universal consensus, actually, and there's some disputes on this, but whatever. This is my talk, I'm just going to say what I think about it. When I think of how I think of mathematical physics, it's like a collection of sub-branches in pure and applied mathematics that are devoted to creation and development of the mathematical skeleton of some theoretical physics, or not necessarily theoretical physics phenomena. So yeah, I see it in like two ways. So one is, in like two branches. One is like explaining what physical phenomena has been been studying for years, and like giving it some kind of mathematical skeleton and connect and bridge very different areas in mathematics. But this is like, it's more of a going from the physics to the math, but actually the opposite can also happen. Because you can also try to take, to advance the mathematics, to try to make some new physics. Some examples of what happened, when this happens, that I have seen, but of course it's non-extensive. If we go from maths to physics, what I have seen this mostly in power has been in the connections between number theory and string phenomenology. And when concerning physics and math, what I've seen this most at play is when it comes to proving several dualities that involves very different mathematical structures. It can be geometric, it can be topological, it can be algebraic, it can be a lot of things. So what we are doing with these dualities is connecting, bridging these two very different notions, sort of saying, in the shape of, we're using categories. So I think this is what I meant by this is exactly the tool we want to tackle this kind of problems. I'd like to introduce you, just to give you a little flavor of some of the research problems, concerning these dualities. Hopefully interesting for somebody, and that actually are shaped in, are stated in terms of categories. So for one example is homological mirror symmetry, first described at this ICM talk by Koncevich in 1994. So suppose that you have two manifolds, so two of these big surfaces. We can say that they're mirrored if you take one of these manifolds, take the algebraic, some algebraic geometry, how can I say this? Take some algebraic geometric notions that you can extract out of it, and then you will get what the experts call the boundary category of coherent shapes over X. And Y, do the same thing, but instead of using algebraic geometry, construct a very different category using symplectic geometry. This is what is usually called the Fukaya category. So, what mirror symmetry states is that these two should be the same. This, it's not so crazy. It's like actually based in string theoretical predictions, has been proven in several examples, has been a very active field, very beautiful. And actually this book, by mirrors, I am sorry for the spam, but actually, if you're curious, this is a very beautiful book to read more about it. Another duality, this is like self-promotion, sorry about that. It's what is called the Landau-Ginzburg conformal field theory correspondence. This is based on research done in the late 80s and early 90s in the physics literature by a bunch of people. So Bafa Warner, Peter Ho, Peter West, Emil Wachtinek, and God knows a ton of people. And then actually I did my PhD on proving the first mathematical examples of this, proving that two categories constructed out of two very different things were actually equivalent. What do we have? On the one hand, we have some categories constructed out of the algebras that actually describe the symmetries of some physical theory. To be concrete, of some conformal field theory. This is some physical theory that displays conformal symmetry. This is on the one hand, and on the other, I'm constructing a category out of some polynomial that characterizes some physical model called the Landau-Ginzburg model. So there is a way of extracting, categories, in these categories from these very two different areas and match them together. Again, this comes from string theory literature. And again, there's some several mathematical examples proven. And if you're interested, I can just talk about it for ages. And actually I'm talking about string theory all the time because it has been like more, it's like the most active area where, mathematics and theoretical physics interact, but actually there's some others, other kinds of dualities. For example, ADS-CFT has more of a geometric interpretation, and it's not exactly string theory based. Also, this has been about dualities, but I also would like to give you another example where we are using categories to formalize some physical notions. So it's just to give it some proper mathematical description. Best example, topological field theory, first described by Atiyah and Siegel. What we are doing here is defining some functor. It needs to satisfy certain conditions. It needs to be symmetric monoidal, meaning there is some tensor product, and it needs to satisfy certain conditions. And this function kind of mimics what we would like to have in quantum gravity. So suppose that as the source category, you have a category whose objects represent space, and the morphisms are going to be space-time. So an example of this is 2-cop. I am being really in the surface. And what I would like to do is like whenever I compute some kind of invariant, I take this if I take any object in here and see, and I want to assign some value to it, for example, some correlation function or a partition function, whatever, then I need this category to have a tensor product, and I have some freedom to choose the best that suits my purposes. I can have vector spaces. I can have the category of, for example, if anybody's familiar with it, of Hilbert spaces. So there. I mean, so what we assign to a certain space-time. I mean, a space and space-time a certain value. Low-dimensional cases of topological field theories are well understood. I mean, in one dimensions, if we consider the category of one-dimensional topological field theories, so it will be a category of functors. This is, one can prove that actually this is equivalent to vector spaces. So it's like, see, I mean, this is like a very complicated structure technically, but you know that actually this is just the same as playing up and down in a category of vector spaces. How cool is that? Okay, let's go one dimension higher. And then if we want that's the same, take all these functors, create a category out of it. You can prove that it's actually equivalent to a certain category of algebras. So it's like a little bit more of a than the category of vector spaces. I mean, so it's, I mean, you need an algebra structure and then some, I'm adding here some adjectives, commutative and Frobenius. And you, again, I mean, you have kind of a fairly complicated thing, but again, this is equivalent to something much nicer, something much simpler. So, which is one of the magics we can do. Actually, and this is mostly what it's not. I mean, there's some cases of three-dimensional topological field theories that are actually in one-to-one correspondence to certain kinds of categories that have a lot of structure. And actually they're beautiful and arise in a ton of places in mathematical physics, but actually beyond that, the classification is wide open. And I mean, and we're only in dimension 3, so this is related to the classification of manifolds in dimension 3. I mean, it's like a brave new world, but beautiful thing, because it's actually giving a lot of, I mean, not only allows for a very nice classification, even if it's only a lower dimensions, it also, I mean, it stimulates a lot of research involving not only, I mean, geometry, topology, algebra, everything together. And actually, I mean, just to finish, maybe, beyond categories and functors, remember these objects that we have with categories that reduce to known definitions? I mean, so these algebras. Actually, these particular kind of objects, I mean, they are important because they also appear in a ton of topics in mathematical physics. So one example is these topological field theories, these functors we just defined, where you're putting some kind of extra spin structure in your manifolds. This is something that worked out by my PhD advisor and my PhD brothers. For example, if we make some extension of the algebra symmetries, describing the symmetries of some conformal field theory, some extensions of some algebra behind the interactions in some physical theory. This is also described and in one-to-one correspondence to algebras in some categories. Again, I mean, Juan, Kirillov-Lepolsky, Krotik, Canada, Wraith for the super case. For example, I mean, they also appear in terms of, I mean, whenever one wants to describe boundary conditions of some topological field theory which has conformal symmetry. Again, also work from my PhD supervisor and others. And I mean, that's it. I mean, this is actually a non-exhaustive list. If you're curious, please talk to me, email me, let's talk about it. But I mean, I hope I still have convinced you that this is a very fun and a very powerful algebra tool that allows us to tackle a lot of problems in mathematical physics and gives us like a brave new perspective of everything we can do. Just be aware of the rabbit hole that if you start like doing categories of categories of categories of categories, well, just kidding. I mean, just rabbit hole and enjoy categories as they are. They're amazing. They're beautiful. Or in any way like. And I guess that's it for today. I guess I'm a little bit early. Diolch yn fawr, I mean, as we say here in Wales. And if you have any questions, please, I will be very happy to answer. And if not, please don't hesitate to drop me a line at roscamacho at cardiff.ac.uk. Thank you.
Thank you, Ana, for the talk. Muchas gracias, Ana. We like to see if we have some comments or questions. So let me see. Hearing comments. Okay, I don't see any questions or comments.
Can
Okay.
can guests Nada, muchas gracias.
Okay. Thank you very much, Ana. It's a pleasure to have you here.
Yeah, thank
Ana
you
es
again
una
for the
de mis
invitation.
colaboradoras más preciadas y queridas, así que para mí
Oh.
es espectacular tenerla acá. Espero más adelante poder vernos presencialmente. Muchísimas
A ver si
gracias.
puede ser pronto. Thank you.
Y le cedo la palabra entonces a los organizadores.
Dele.
So I think it's now up to me. According to the schedule, the next talk should start at 9:20. But I don't know. Andy, are you ready? So we could maybe start sooner?
You should stick with the scheduled time, because otherwise people may miss the beginning.
Yeah, you are right. Exactly.
Yeah.
You are right.
Is Anna still there or not? I can't see her.
They have to put her back
I
in.
am.
Thank you, Anna. You set up for my talk beautifully.
Exactly.
Because
Great. That was
many
not
of
really
the things
intended.
you talked about are good background for my talk.
Yay.
It's a good job we switched the order, because it's better this way round. So yeah.
Awesome. Glad to help.
Yeah, I really like you're right about Emily's book. It's full of really lovely examples, and what I particularly like, when I got that book, I looked at her examples, and I kept finding examples either that they were the sort of examples I would have used, or discovering examples I'd never seen before. She has a really good sort of collection of interesting examples, and
I love it. I mean, and I find it so powerful. I mean, it's just. I mean, it conveys the message so well, and it's worked out in detail. So students, this is available for students. It's not like any technical thing. I mean, you really can go like completely clueless and get out like more.
Gail, have you seen Emily Reel's book?
I have not had a look at it.
It's really nice. You can actually download it. I think she's done a deal with the publisher.
Actually, I think I have downloaded it already.
Yeah, right.
But not had the time to look at it.
It's an ideal thing to give to a beginning graduate student. I mean, probably you and I grew up on things like Maclean's book. I mean, I actually grew up on Maclean and Berkoff's book, actually, as an undergraduate. But I mean, Maclean's Categories for the Working Mathematicians is a great source, but Emily's book is so much better in terms of motivating examples and things. I mean, I've nothing against Maclean's book, but I think she just does such a great job of picking the right example to illustrate things.
Yeah, absolutely agree.
Yeah.
So are we winning over people to higher category theory right now?
No, that's not what I'm saying. No.
No.
Just aware of the rabbit hole.
Higher categories.
Yeah, actually, I mean, the highest I go is 2 categories, so I'm not going to go any higher.
Yeah, that's about my limit as well. Yeah.
I prefer to work out like more in the detail and like internal structures and the such. So yeah. I mean, it's interesting. It's definitely cool, but just not my jam. I mean, like, this is an amazing thing. Just keep it cool. That's it.
My collaborators always tell me that people already work in higher category theory. They just don't know it.
They just don't know, right?
That's true.
The worst I have seen this is like somebody from my alma mater, like telling this to a bunch of theoretical physicists. It's like, you have been doing categories all the way since high school. And it's like,
Well, I mean, in my talk, I'm going to talk about Massey products, and that's a really nice example of exactly this philosophy that, passing through an equivalence relation is what you usually do. But there are some times when it's very useful to be able to go the other way. And in a sense, that's what higher category theory is largely about, keeping that additional structure there to use when you need it. And it's a very subtle recognition of why that's useful and when it's useful, And,
I mean, one also has to say there is a difference. One can talk about higher categories.
Yeah, I know, but
and then there's the theory of infinity one categories, which by now is so well established that you can basically do ordinary category theory in infinity one categories.
Yeah. But what I was really meaning was that when you factor out by homotopies, usually that's presented as the right way to go. But
no. It's
often remembering the homotopies is a
exactly
very useful bit of structure that you shouldn't completely forget.
You do that. You factor out homotopy only at the very last step when there's nothing else to do.
Well, but Massey products are really exactly this phenomenon of keeping it there to use when you need it. It's sort of a good example of why that's a useful phenomenon. Yeah.
I have a quick question for Anna.
Tell me.
The motivation for your work, is it actually coming from string theory, or is it coming also from other parts of mathematical physics?
To me, it has been mostly string theory. Like, for example, this correspondence I talk about, the Lambda-Ginsburg CFT correspondence, that's, string theory, topological D-branes at most. All the rest, since then, I have been migrating more into, let's say, more purely mathematic topics. But, that has been my biggest source of inspiration so far. I still enjoy reading more. Reading about it. It's just that mathematically, I'm just like focused on the quantum algebraic aspects of it. Since
okay.
Having fun. At the end, I can tell you about it.
Do you know people in Glasgow? Do you know
Greg Stevenson?
Sierra
Graz.
Yeah. Well, they're in Cambridge at the moment.
Yes, and that's true. But
yeah,
wait, but they were lecturers there, right?
You know Christian Korf?
He recently won an EPSRC standard award with one of my colleagues who is like years away, Simon Wood.
Yeah. He's probably the closest sort of physicsy person.
He works in integral.
There are lots of people doing integrable systems who sort of touch on things like vertex algebras and things, but he's the person who's most sort of closest to sort of the algebraic physics interaction.
Yeah. Looking forward to meet him. I guess that he will visit Simon up and down when. For the duration of their grant. There should be some postdoc. We should be sharing some postdocs between Glasgow and Cardiff. So.
Yeah. Right. Yeah.
Nice to meet you. And I guess that it's time for your talk. 18 past.
Yeah. Well, when you're ready, let me just try to share first of all.
Exactly.
Yeah, I was going to suggest that if you want to start sharing.
No, I think I did
it works
with the window. That's right. Yeah, I did.
Thank you, Anna, again.
Not a problem. Thank you, guys.
Hola, Anna. Hi, Anna.
Hola.
Can you hear me?
Yeah.
Okay. I have a small question. Sometimes we try with Adriana to construct some category, but we have considered the object formation of finite soluble groups, but it was very complicated. Do you know if there exists some construction in this direction?
Not completely sure. Like finite and soluble.
Yeah, the formation of finite formation. The objects were formation of soluble finite groups. It was really very complicated, but
yeah, I mean, I think so. I mean, I can guess so.
oh,
Not completely sure. I'm aware of a good reference
okay.
to point you to. But
Okay.
I mean, if I come across something, I will let you know.
Okay.
It's an interesting one. Why do you want this one in particular?
Okay. This is a big part of finite solvable group theory, and you can extend this result to algebras, for example, Lie algebras or Jordan algebras, or in general non-associative algebra. But the idea was to construct some category in this context, that the object is very clear. This is formations of groups, but for example, the arrows and functors and some that is
I mean the arrows. I'm not so sure. Yeah, I mean that would be my. I mean, Adriana, you here? Adriana?
Hola, Adri.
Okay, doesn't matter. It's just
okay, it's
maybe.
Okay.
No, I mean, I was wondering, like, if you, because there are ways and ways of constructing subcategories, and depending on what kind of properties you want to preserve. So I was wondering if there was, like, maybe is there a way maybe of characterizing this, but I'm not completely sure how you will proceed for the case of sublevel groups. Anyways, I will give it a thought. Maybe. Interesting question.
Maybe
nice.
We can talk later then.
Yeah. Okay.
Good. Thank you. Okay.
Not a problem. Thanks to you.
Okay. Thank you. Go ahead, Georg.
Okay. Well, so my name is Georg Biedermann. I'm a professor of mathematics at Universidad del Norte, and I'm very happy to present Professor Andrew Baker. He's from the University of Glasgow. And his field of interest is a very wide one, from number theory via representation theory all the way to stable homotopy theory. That's actually where we got to know each other more than 20 years ago.
Yeah.
And so the title of your talk is Numerical Polynomials, Common-Congruences, and Massey products. And there you have it, from number theory all the way to stable homotopy theory. Okay. Andy, please take it away.
Okay. Thank you. Well, it's very nice to be able to talk at this. I've only ever been to South America once, to Argentina, so this is a new destination. Now I'm a bit confused about my sharing. It doesn't seem to be. Why is it not? Okay. Is that coming up? Why is it not sharing?
Maybe you can do it again. I don't know.
Yeah, I think something's happened to it. Yeah, let me try it again. Maybe what's happened is right. It's sorry. Let me try again. Share.
Okay. Let's wait a moment. Yeah,
good. Right. Thank you. Right. Okay. So now it's rather good that Anna's talk was before mine, because quite a few things she talked about, I'm sort of using similar ideas. I'm not going to make them very explicit, but they are sort of lurking around in what I'm going to say. Now, wait a minute. I have a problem. I see. Oh, that doesn't work. Sorry. I have to figure out how to move around in my slides. So this, right, that should have taken me to the next page. Is that right? Yes, good. Okay, so what am I talking about? Well, I should say that the Georg's view of my career is sort of backwards. I primarily think of myself as a stable homotopy theorist, but I use algebra and number theory ideas a lot of the time. So my motivation is kind of backwards. I'm sort of an applied mathematician in some sense. And so historically, the reason I've been interested in these ideas for about 40 years is that they came up originally in my thesis and then in a big project with 4 other people. In fact, they were mentioned on the last slide. Francis Clark and Nigel Ray and Leonor Schwartz. And we published a paper around about 1989, which includes a lot of these ideas. But every so often I come back to this, and recently I've been thinking about the Massey product part of it. Okay, so the starting point is some very basic objects. These are monoids. Now, for those who are not perhaps familiar with this, a monoid is like a group, except you don't necessarily have inverses. So it's got an associative product with some kind of identity. In this case, they're commutative, but not necessarily with inverses. So there are 2 very basic examples. The natural numbers, and I'm going to include 0 in n plus, and the non-zero natural numbers. The first operation is addition. The second operation is multiplication. And of course, you can what's called group complete these. The smallest group containing the additive natural numbers is the integers. The positive rationals is what you get by group completing the multiplicative natural numbers. But we also want, for many purposes, want to throw in negative rational numbers. So the multiplicative group of rational numbers, non-zero rational numbers, is the obvious sort of group completion that you're probably more likely to think about. Okay, now I want to think about certain types of functions on these. And the simplest functions you can probably think of are the polynomial type functions. So I'm thinking initially of rational polynomials, and I can plug in a natural number and I get a rational number out. Later on, we're going to be doing the analogous thing for non-zero rationals, and I'm going to want to invert the variable, but I'll come back to that later. Now, the first thing I'm going to do is look inside of the polynomials, the rational polynomials, at functions on the non-negative integers, which if I plug in, I shouldn't just get a rational number. I'm going to look at the ones where I get integers as the output. And if you think about it, that gives me a subring of the polynomial ring. And there's an obvious subring of that, the integer polynomials, but there are lots more interesting elements in there. For example, the binomial coefficient functions. These are very combinatorial objects. These are polynomial functions in the top variable. Of course, when you expand them out, you get rational polynomials, you get lots of denominators. But when you plug in a natural number, these give you integer answers. In fact, of course, they will give you non-negative integers. Now, those come from combinatorics, but now there are some number theoretic examples. Euler's theorem says if you take a natural number n, you take any integer x, which is co-prime to n, raise it to the phi of n, subtract 1, then that is always divisible by n. That's Euler's theorem. But if you don't want to insist that the GCD of x and n is 1, you need to put a power of x in. And in fact, you can figure out what the smallest k is. It really only depends on the prime powers that divide n and the highest power of any prime that divides n. And that is the smallest possible k that will work there. And of course, special cases of that will give you things like Fermat's little theorem type polynomials. Okay, now there's another kind of operation you can do. You can take 2 polynomials that live in A, and you can substitute one into the other. And this is a little bit less obvious, that if you do this, you get something else which is in A. This is not quite immediate from what I've said so far, but it's very easy to prove it. So these things have lots of interesting elements, and the ring structure is very interesting, particularly if you reduce mod n. The algebra structure has lots of interesting congruence type conditions amongst elements. Now, there's another kind of element which I'll mention. These are the so-called Bernoulli polynomials. These are rational polynomials in X. There's one for each n. And these are the things which come up when you try to write down power sum formulae. If you sum up the first r-1 nth powers of integers, of natural numbers, there is a formula for that, which is a polynomial expression of degree n plus 1. It's a rational polynomial. And these Bernoulli polynomials are basically the things that you get. You have to subtract off the constant terms. Now, if you've never seen these before, certainly the first few values of n, you meet these in elementary courses, but you may never have seen the very general version of this. These can be computed by a generating function, and the constant terms are the so-called Bernoulli numbers. So these things are, very important. They come up in many, many places in mathematics, not just number theory. The reason is that if you take d by dx and think of the operator e to the d minus 1, and you apply that operator to a polynomial, it's the difference operator. You add 1 to the value and subtract the value at x, and you get a polynomial of 1 degree less. I'm going to say a little bit more about that in a minute. But these Bernoulli numbers, the odd ones are almost all 0. The even ones are the ones that are interesting. And I've written down the first few Bernoulli polynomials with these denominators in, and down the right-hand side, you see the constant terms, which are basically Bernoulli numbers divided by just, Bn over n type expressions. What's interesting about these is when you look at the prime power factorization of the even ones, you discover all sorts of remarkable things. For example, B12, you notice all the denominator prime factors occur to a single power. On the top, there's this rather mysterious number 691. This is actually a prime. So when you look at the numerators, there are some rather surprising occurrences of quite large primes. They just sort of pop out in the middle of nowhere. And they're much less obviously understandable than the denominators, in fact. Now, for what I'm going to say later, I'm actually going to find it useful to use the convention that for negative n, Bn is minus B minus n. That's just a convention that puts in a sign that's quite useful in various formulae. Okay, let me say a little bit more about these Bernoulli numbers. And this is all to do with the way the prime factorizations of the numerator and denominator. So there's a standard concept for an integer. The power of p that divides an integer is often written nu sub p of n. It's the maximum k such that p to the k divides n. And then you can extend this to a rational number. You can look at the difference of these for the numerator and denominator. This is a well-defined integer. And then there's a theorem which is usually attributed to some subset of Clausen and von Staudt. That's two people, but there are various papers by them which prove various parts of this statement. So I think there's even one joint paper, in fact. But so this tells you about the denominator of a Bernoulli number, an even Bernoulli number. It says it's only the new p for it is positive only when p minus 1 divides 2n. And in that case, you get exactly 1 power of the prime dividing the denominator. And we've seen an example of that earlier for B12. And then a rather sort of better statement is for the denominator of B2n divided by 2n. And this formula gives you the precise powers of p. And of course, it depends on the power of p dividing n, but then you get, for an odd prime, you get 1 more power, but for 2, you get even better. So these are precise statements about the powers of various primes dividing the denominator. and, you know, in the prime factorization of the whole rational. Okay, so let's go back to the rings of numerical polynomials. I'm going to generalize. You can do this sort of with n variables. A to the n is the analogous gadget for polynomials over the rationals in n variables, which map n tuples of positive natural numbers to the integers. That's an obvious generalization. When n is 1, we get A itself. And then there's a big theorem which contains several interesting statements. Firstly, if we take the case of A itself, what is it as an abelian group or a Z module? Well, it turns out to be a free abelian group with the Cn of x's, the binomial coefficient functions, as one particular basis. The other thing is, and this is why I was careful to talk about monoids and then those groups, you can always extend A, thought of as a function on the positive integers, the natural numbers, to an actual function on the integers, which maps any integer to an integer. So it would have probably been better to start off with that as the definition, but you know, I just wanted to emphasize that we can start with a much weaker thing and then we get something about functions on a certain group. And then, well, here's the other statement that's a little bit looks a little bit more complicated, although actually the proof is basically the same idea as the proof of part A. A to the n is the functions which map n tuples of integers to integers. And as a ring, this is isomorphic to the n-fold tensor product of A with itself. So that sort of describes what could be a very complicated ring in terms of something which we maybe should regard as understandable. How do you prove this? Well, the proof of A and C really depends on using this difference operator together with Pascal's triangle, which tells you that when you apply delta to Cn of x, you basically get Cn minus 1 of x. That's essentially what Pascal's triangle says. So you use that to do a sort of downward induction on degree to prove these kinds of things. Now, the natural numbers under addition, you know, you have this this addition pairing, this function from 2 copies to 1 copy, and this, because we're looking at functions from something into a fixed ring, because it's essentially a sort of contravariant functor, we get a map going the other way. It goes from A to A to the 2, which is really A tensor A. And there's something else you can do. You can take one of these functions and evaluate it 0, and that gives you an integer. So this actually gives you, we already know we've got a ring, or in fact a Z algebra, but it gives you a coproduct and a co-unit. And this is a structure called a, well, in English, it's usually called a bialgebra, but if you're precise and if you're French, you might call it a bigebra. The French know enough about Arabic to know why bialgebra is a little bit wrong. The English speakers probably don't. Now, in fact, there's a little bit more going on here. That's to do with the fact that we can really think of these things as functions on a group, which means we have what's called an antipode. This is, here everything is commutative and co-commutative, so it's an algebra automorphism, which is part of the structure of what's usually called a Hopf algebra. So this is actually a bicommutative Hopf algebra. And you can see the structure very explicitly. The coproduct, you send f of x to f of x tensor 1 plus 1 tensor x. You just expand that in terms of the binomial coefficients, tensor 1 and 1 tensor binomial coefficients. The co-unit, you just evaluate it 0, and the antipode just sends x to minus x. So, for example, if you work out what the coproduct on Cn of x is, it's just this standard sort of bilinear combination of tensor products. That's a very sort of standard formula called a binomial coproduct. All right. The other thing we can do, I mentioned this earlier, is we can invert X. Now, if we just take A, we can just localize. We're talking about a commutative ring. So there's a well-known procedure of localization by inverting X. And this sits inside the Laurent polynomials with rational coefficients. And this is a more interesting gadget for all sorts of reasons. So here's an example of a family of interesting elements in it. These are things involving Bernoulli numbers, but you notice I've got an extra power of 2 in the bottom. So if I take x to the 2m minus 1, that rational multiple of it turns out to live in this a with x inverted. Now, what that really means is if I multiply by a very high power of x, I get something in a, right? So I get an actual numerical polynomial. But this thing doesn't really live in the ring of numerical polynomials until we multiply by some high enough power of x. Okay, and that again is due to Clausen and von Stout, and also Frank Adams, a topologist, who kind of discovered this as well. All right, so now I can give you a rather slightly harder theorem to prove, which is really a theorem from topology, although it's based on number theoretic ideas. It's due to various combinations of Frank Adams, Harrison, Switzer, and then part of it is due to Adams and Clark, my co-author. So the first thing is we can interpret A with x inverted as a ring of functions. You can think of it as functions on the non-zero natural numbers, which when you plug in a natural number, it doesn't give you an integer. It gives you an integer, but you may have to invert t. So it gives you a rational number, but the denominator only involves the primes dividing t. Right. So that sort of depends on what you plug in. So it's not a kind of uniform thing. If you think about this a little bit more, you discover that we can say it in a different way. This time we're allowed to take rational numbers, so a over b, where b is non-zero. What happens when we plug a rational into such a polynomial? Well, the answer is not quite an integer. It's an integer over something which may involve the primes dividing a and b. Okay. Again, it's a little bit more complicated to say that. Now, the third part is due to Adams and Clark, and this was a little bit surprising because people didn't think this was true for a long time, at least Frank Adams didn't. It's actually itself a free module over the integers, a free abelian group with a countable basis. It is a countable ring, so it has a countable basis. And that's much less easy to prove. And finding explicit bases is a big sport. I mean, there are a lot of people who've written papers about very specific kinds of bases. There is no really easy way to construct bases for this. The final thing I want to say is that this is also a Hopf algebra, but this time we have a different coproduct. It's the one that sends x to x tensor x. It makes x what's called a group-like element. And this time the co-unit is not evaluating at 0, but evaluating at 1. And the antipode sends x to x inverse. Okay. Now, you can sort of play around with this a little bit more. I'm perhaps not going to spend time on this because it's not so important for what I'm going to say. But basically, you can think of n times as acting on n plus by multiplication. And you can think of each element in n times as acting by a group, by a monoid homomorphism, and you can extend it to an action on the integers by group homomorphisms. Unfortunately, you can't quite extend this to an action of q times on it, of course, but sort of morally, that's what you're really trying to do there, but you can't quite do it. What you do have, however, is, for those who know about Hopf algebras, we've got a Hopf algebra A, but we've now got a coaction of another Hopf algebra on it. So this big psi is really meant to be a sort of coaction of A with x inverted on A. So this actually makes it into what's called a comodule algebra. There are some other things you can try to do here to do with dualizing. And this is to do with the fact that lurking in the background, we're really trying to make some sort of sense of the group ring of Q times. And in a certain sense, A with X inverted is trying to be the dual of that group ring, except it's not quite. It's only really the dual when you tensor up with the rationals. And this is what makes it quite subtle to talk about this. Okay. Now, for those who know about localization as in number theory and algebra, one thing we can do if we really want to understand things better is to work with one primer only. And the way you do this in algebra and number theory is you fix your prime and you invert all the other primes. That's a standard procedure that you can do in commutative algebra. So you get these localized rings, and not quite the same thing, but there is something else you can do. You can form what's called the p-adic completion of the integers and the rationals, and you get the ring of p-adic integers sitting inside of the p-adic numbers. In fact, ZP is the unit disk in QP, which is the Cauchy completion of Q with respect to what's called the p-adic norm. Now, if you don't know about that, don't worry too much, but ZP is a compact, complete local ring, and the units in it form, well, it's both closed and open. It's a Clopen subset of ZP. Now, all of this sounds a bit weird because we're talking about a non-Archimedean norm here, which doesn't behave quite like the usual notion of norm in the real numbers. Okay, now why have I mentioned all of that? Well, it's because we can interpret this localized version of A as polynomial type functions on rational polynomial functions which map the p-adics into themselves. So this sits inside of QP of X in a very obvious way. And if we invert X and localize it, we can commute the two localizations there. We can also think of this as the Laurent polynomials which map p-adic units into the p-adics. So these rings have a very nice interpretation in terms of very sort of specific types of functions. And if you complete these with respect to the sup norm, you get all the continuous functions from ZP to ZP or from ZP times to ZP. So these things are kind of dense inside of these big rings of continuous functions. In fact, the locally constant functions are also dense, which is another sort of weird fact about these kinds of topologies. All right, so let me see, how am I doing for time? So I've had about 20 minutes, haven't I? Oh, wow, I need to speed up. Okay, bit more number theory. I've mentioned these these Bernoulli number things. So I want to mention some, really these are congruences amongst Bernoulli numbers. So the sort of prototype version is the one I've written down, where I've got a particular prime in mind. And you notice what I've done with the Bernoulli number terms is I've got 2m here, and here I've added on p minus 1 times p to the s minus 1. So there's a kind of shift in the index to do with p. And then it's a fact that if I look at that difference, it's a rational number, remember. If I divide by p to the s, I get a rational number whose denominator does not involve p, right? So it's a p local integer. It's almost an integer. The denominator is not divisible by p. Okay. Now, these kinds of congruences were known back in the 19th century, but the point about the language I've set up is it's very nice. It's very convenient to sort of encode these as a kind of operator between A and A with X inverted, a group homomorphism. So the global version is just a homomorphism from A to A with X inverted, and it sends X to the N to, well, we saw this earlier, at least up to a power of 2, we saw this earlier. So there is a group homomorphism which behaves like that and in particular on powers of x, it gives you that. Now, there's a more refined version which depends on the choice of a prime, and this is due to Kubota and Leopold, and then was formulated this way by Nick Katz. And the main difference is this Euler factor, 1 minus p to the n. If you know about Euler factors in number theory, this might look familiar. That's a sort of correction term, which is to do with the fact that we're working somehow with p-adic units rather than arbitrary p-adics. Okay. So, as I say, the number theory underlying this requires a version of p-adic integration and p-adic Bernoulli measures, and sort of appeared in the 1970s originally in this form. Now, this is a useful idea because it means you can construct elements in A with x inverted sort of iteratively. What you do is you take kappa of something. That's a Laurent polynomial. You multiply by some high power of x, you get a polynomial, so you can feed it back into kappa and get something else. And you can keep doing that over and over. And this allows you to generate really interesting elements. So, for example, kappa applied to this thing, if you think about it, this is a numerical polynomial if a is big enough. And this gives you, this gives us that extra power of 2 that I mentioned. So you can sort of get that because you can put a factor of 2 in the denominator in the domain object. So that produces this extra 2. So you can then bump up this by some x to the b. And, well, if you feed that into kappa, you get this thing which involves sort of bilinear combinations of Bernoulli numbers, and that is in the stably numerical polynomials. So this is a way of producing deeper and deeper elements which encode what are usually called the generalized Kummer congruences. It's the fact that these are in some sense numerical or integral as functions that is really capturing a lot of congruences amongst Bernoulli numbers. You can plug in values for x that are carefully chosen and you get an actual statement about some rational number being integral. Okay. All right. Now, I haven't got a huge amount of time, have I? All right. So I wanted to just talk about how you can apply this to compute something in something which is a very fancy gadget, the cohomology of a Hopf algebra. Now, here we're talking about very specific examples, but the general story is that if you have a Hopf algebra over a commutative ring, provided it has enough conditions, particularly flatness, there is a sort of Hom functor. You can Hom from this as a comodule into another comodule, and that is left exact, and so it has right derived functors, some sort of cohomology functors. And as always with cohomology, you can compute it in various ways using resolutions, injective resolutions, or an explicit complex like the Kobar complex. Okay. Now, in this case, I'm really only going to talk about the Kobar complex. The Kobar complex is very explicit chain complex. In degree S, you write down, well, I'm going to be doing this for a comodule algebra, but you write down B tensor a lot of copies of H with a very specific differential that some of you will recognize from various contexts. And then the cohomology is this coexed gadget. Okay, so that's sort of standard, really. Now, if I plug in the things I've been talking about, so I could take K to be Z, H to be A with X inverted, and well, for B, I'm going to take a very specific thing. It sort of looks like a polynomial algebra on a variable U, but I want to think of that as in a grading 2, and this is sort of a graded gadget. And if you do that, the coex turns out to be itself a graded algebra. But the fact that we've got a grading on U and powers of U means we've got a secondary grading, a sort of internal grading, which kind of is there, right? And now I can tell you what this looks like in low degrees. And if I invert 2, this is basically the whole story. But if I don't invert 2, I have to be a little bit careful because there's lots of additional torsion that I'm not telling you about. So firstly, in degree 0, there's really only one bit that shows up, the stuff when the internal degree is 0. And there you get a copy of the integers. The most interesting stuff is in cohomological degree 1, and in degree 2n, well, it depends on n. If n is odd, you get a z mod 2. If n is even, you get z mod the denominator of this Bernoulli number fraction. And then in degree 2, there's one group that shows up in internal degree 0. It's a huge group. It's Q mod Z. Now, as I say, if I invert 2, that's it. But if I don't invert 2, I actually get a lot more stuff that I don't really want to get into. Well, you can even write down what generates these degree 1 things. The most interesting things are when n is even, and you get these Bernoulli type polynomials coming up. So all of this was sort of proved back in around about 1970 or thereabouts, and then reproved by various people later on, Bousfield, Ravenel, and so on. Okay. How much longer have I got? I've really run out of time, haven't I, Georg? 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 Well, okay.
Andy, can you hear me?
Yeah, sorry, have I run out of time, or have I got
you have like 8 minutes, 9 minutes?
Oh, okay, all right. I thought it was a bit over. All right. Okay, so I want to just illustrate how you can use these to do computations in these coext groups. And this involves the idea of Massey products. Now, I could spend a whole talk on Massey products, but Massey products occur in the cohomology of a differential graded algebra. Now, what is a differential graded algebra? Well, it's a graded module over some commutative ring with a differential which shifts degree up by 1. And when you compose consecutive ones, you get 0. So it's a chain complex. And that means, of course, that you can define cohomology. In each degree, you can take the kernel of the differential mod the image of the next one down, and you get these cohomology groups. But here we're putting in extra structure because we want the multiplication to interact with the differential in a certain way. It obeys what's called the Leibniz law, or the Leibniz rule. So this is basically the formula for differentiating a product. There's a slightly weird sign. That's a standard sort of sign that crops up in graded, in chain complexes. So I won't explain it, but it's just there for various reasons. And what you can do in the cohomology of a DGA is multiply. If you take a coset of A and a coset of B, there is a product where you just take the coset of A times B. If you think about it carefully, you'll see that that makes sense as a multiplication in the cohomology, and the cohomology turns out to be a ring. Now, what are Massey products? Well, you see, if we were just in a ring, then knowing a product is 0 you can't really do a lot with that. But in this setting, if we have 3 elements, and I'm calling these the cosets of X, Y, and Z, if the product of X, the first 2 is 0 and the product of the second pair is 0, then we can define what's called the triple Massey product, and it's written with angular brackets, and this is defined to be a coset in a particular degree. The degree here involves the degrees of the 3 elements you feed in, but it is this indeterminacy subgroup is got by sort of multiplying things by X on the left and things by Z on the right, and that is a subgroup, or more precisely a sub K module of this particular cohomology group. But how do I get a representative for this coset? Well, I have to define a W explicitly. So what I do is I first find something whose boundary is x times y. That's possible because this product here is 0. And then I do the same thing with the fact that yz, the cohomology class of yz, is 0. So I can find something that allows me to write yz as the boundary. And then I take some combination of those with a sign. Again, the sign is a little bit weird, but it's put in to make things work properly. And if I do a calculation with the Leibniz rule, you'll see that actually this is, when I apply delta to this, I get 0. So this itself represents a cohomology class. So the definition of the Massey product is it's a subset of this cohomology group. It contains this element I've constructed, but it also contains that with all the things in this subgroup added onto it. So it's not an element, it's a coset in a K module. Okay. And the indeterminacy is exactly coming from the fact you've got choices. For example, I could vary my choice of U and my choice of V, and that variation is adding on things that the boundary maps to 0. So that's really where the indeterminacy comes from. So this is a clever way of constructing new elements using, it's essentially homotopy theory. And we were talking a little bit about this earlier, about higher category theory. This is sort of an appearance of sort of higher categorical information. All right, so how do I use this? Well, I can actually compute some Massey products now in coext1. And this depends on spotting some formulae. For example, what is the product of these two representing elements for things in coext1? Well, the product formula is a little bit strange because it's a formula in the Cobar construction, which is really standard, but it sort of looks a bit weird, but this is the way it works. And now what you observe is that if you feed in this bilinear thing, that's the sort of simplest example of a Kummer type congruence Laurent polynomial, hit it with the boundary, what do I get? Well, I get exactly the thing I've written up above corresponding to the product. So that's where you begin to see some interesting observations using the Kummer congruence type polynomials. And the other thing you have to do here is write down, well, it's this integer, the numerator of this Bernoulli number term, times this power of u. And when I work out the boundary of that, I get the numerator of that thing I said was a generator earlier. So if I do the calculation, what I discover is that, okay, what is it saying? Well, the first term here is an integer. So this is really in coext 0. Remember, I said coext 0 in degree 0 was a copy of the integers. So that's really in coext 0. This is something in coext 1. This is something in coext 1. So this Massey product makes sense because I've shown you that when I multiply these together, I get 0. I've written the product as a boundary. So when I do the calculation using the formulae I gave you, I discover I actually get this as a representative. But of course, it's not the only representative because I have to add on things in the indeterminacy, which I'm not going to bother to do explicitly. So this is a particular element. And when you look carefully at this, you remember that the numerator is supposed to be co-prime to the denominator. So if you think carefully about it, you'll see that this is essentially co-prime to the denominator here. So this is basically a generator for the corresponding coext1 group. I mean, you have to think a bit carefully about that, but it basically says that when I form the Massey product, it contains the generator. Okay. Now, there's a history behind this. I mean, Frank Adams calculated things like this back in probably the late 60s or early 70s. What he didn't know about was the precise form of the Kummer congruences. So what I'm contributing is a little bit of extra number theory. Okay. All right. Well, gracias por su atención. And if you're really interested, there are some references that I'll leave up there. Okay, I'm sorry I overran a bit.
We also started like 3 minutes late, and so on.
Yeah, I lost track of the time. I'm sorry.
Yeah. Okay. Thank you for the talk. I don't know if anyone wants to ask a question, because I would have a little question, but maybe someone else has a question. Well, I'm going to ask my question.
Yeah.
These coex groups that you had there.
Yeah.
I think they should be an E2 term of a spectral sequence, right?
They are.
And you are calculating massive products in some spectral sequence.
Yeah, that's right.
In the E2 page of it.
Yeah.
What spectral sequence is it?
Well, it's okay. So I mean, this is why
where does it converge to?
Right. It's the atom spectral sequence which computes the homotopy of the k-local sphere.
Right. Is it the stable or the unstable one?
No, it's stable.
The stable.
This is all stable. Now, of course, since that early work of Frank's, I mean, Frank was trying to do this without the co-module. I mean, the co-module story came along after the J of X4 calculations. This then was sort of reinterpreted in terms of co-modules over this Hopf algebra. The calculation was sort of, with two inverted anyway, was done by a student of Frank's called David Baird, but it was never published. In fact, even his thesis is basically unobtainable because it's disappeared from Cambridge's library. However, in the 1970s, the Miller-Ravenel-Wilson paper came along, and they basically recalculated the same thing, except you don't quite see it in that language. More recently, this has all been rejigged in terms of homotopy fixed point spectral sequences for p-adic groups. So in particular, the p-adic units. So this is really to do with the continuous cohomology of the p-adic units acting on some, p-adic representation. And that's almost the same thing. That computes the K1 local version of the sphere. There's a p-adic completion going on there. That's the difference between them. So, there are at least three different ways of thinking about this calculation. And but X1 is basically independent of that. It's really the difference between the X2, and in the completed case, you get another term in X1. That's sort of the only real difference. Yeah. Okay.
Yeah. It's funny that you have in the negative part, you have this Q mod Z showing up, right?
Yeah, but that's sort of, that's the clever bit.
Exactly. It's also in the unstable atom spectral sequence.
I've never looked at the unstable one, but I guess you might get something like that, but I don't really, I don't know.
I think we have to turn now over to Ismail. So thank you very much again, Andrew.
Thank you.
Yeah, well, very nice talk. Quite dense, but very nice.
Yeah.
And I think we should give over now to Ismail.
Yes, I am here. Okay.
Hello.
Hi. Thank you, Andrew. Very nice talk.
Thank you.
Okay. David, are you there?
I'm a bit confused about the timing. According to the schedule, this session is due to finish at 5:15.
Yeah.
Which means there's still an hour and 7 minutes. So I think perhaps Andrew's
we have
been curtailed a little.
Yeah, actually we have 12 minutes too, I think so. But can we start early? Is okay for you?
That's fine for me, yes.
Okay,
yes,
good. Okay. Emma on Fiorella is okay? Can we start now? Okay, good. Good, very good. Good morning to you all. Thank you for coming. It is my pleasure to introduce Professor David Anthony Towers. Professor Towers is an emeritus professor at Lancaster University and his research interests lie in the following areas. First, general non-associative algebras, especially Jordan algebras, Lie algebras, Leibniz, genetic, Bernstein, train, and super algebras. In group theory, Professor Tower works in soluble groups, formation theory, maximal subgroups, and many areas related to the Lie algebras. And even in mathematical education, he works in theory of mathematical learning. Thank you, Professor Tower, for attending this invitation, and go ahead.
Okay, let me see if I can share my screen then.
Okay. Yeah, very good.
Good.
Yeah, good.
Okay, well, first of all, I'd like to thank the organisers and Ismail for giving me the opportunity to speak today. What I'd like to talk about is how certain algebraic structures arise naturally in genetics. And I was unsure of the background of the audience today, so I've endeavoured to keep things as simple as possible. So let me start by giving, no, for some reason that's not, the file is not moving. Or why? Okay, so let me start by giving a brief and simplified outline of some of the basic concepts in genetics and introducing some of the terminology that I'll need later. Now, when I try to advance the slide on the, it doesn't seem to work. Let me go on to there. Okay, so cells of organisms contain chromosomes, which are lengths of DNA, whose structure endows it with two important properties. First of all, it can act as a blueprint for the manufacture of amino acids, and it has the capacity to replicate itself. And this ability to replicate itself is endowed by its unique structure, the famous double helix of Crick and Watson. And during mitosis or cell division, these helices unzip and they separate, and each one acts as a template to which molecules become attached in a unique way, thereby producing a chromosome that's identical to the original. And each of these lengths is a linear molecule that's composed of 4 types of smaller chemical molecules called nucleotide bases. And they are adenine, cytosine, guanine, and thymine. And they're usually denoted by their initial letters, A, C, G, and T. And these are arranged in a particular and a significant order. And this order specifies how the 20 or so amino acids are arranged in a protein, how much is to be made, and when. And a length of DNA bearing information for an unbroken sequence of manufacture of an amino acid is called a gene. Well, we speak of a gene appearing at a particular locus or position on a chromosome. And one of the 23 pairs of chromosomes in humans determines the sexual characteristics, whether or not you're male and female and what's associated with that. And we call such a locus sex-linked. A locus on any of the other 22 will be called autosomal. Now, a gene can undergo change in its internal organization, and such a gene is called a mutation. And the various forms of a given gene are called allelomorphic genes, or alleles for short. And at a particular locus on each kind of chromosome is found only a particular gene or one of its mutated forms or alleles. So let's consider the simple situation of just two possible alleles, X and Y, occurring at an autosomal locus. Remember, that means it's not sex-linked. Then they can combine to produce three possible genotypes: XX, XY, and YY. Because this is an autosomal locus, YX is considered to be the same as XY, as parental origin isn't retained. Now, using this juxtaposition suggests a multiplication, and it's natural to write XX as X squared and YY as Y squared. So let's assume that the homozygotes, the XX and the YY, pass on genes X and Y only, respectively, whereas the heterozygotes, the XY, will pass on X and Y in equal proportions. Then we can write that as a multiplication, as X squared equals X, Y squared equals Y, and XY equals a half of X plus Y. In other words, the probability of passing on X or Y is the same, it's a half. And then we can extend that multiplication to the set of all expressions of the form AX plus BY, where A and B are real numbers, simply by multiplying out brackets in the usual way, just as if X and Y were themselves just numbers. Now, one thing to notice about this product is that it's non-associative. That is, it does matter how we bracket products. For example, if we want to multiply X by Y, then there are two ways in which we can do it. We could multiply the two x's first, so we get X squared Y. Now, X squared is X, so that's equal to XY, and the result is just a half of X plus Y. But alternatively, we could multiply the second X by the Y first of all, and then pre-multiply by X. And the XY, of course, is a half X plus Y, so we get a half X times X plus Y. And now if we remove the brackets, we get a half X squared plus XY. The X squared is X, and the XY is a half of X plus Y. And when we simplify that, we get 3/4 X plus 1/4 Y. So the two results are very definitely different. So this is a non-associative product. Okay, well, in principle, it's possible to count the number of genotypes in a particular population P and find their proportions. Let's say that the proportion of XX to XY to YY is alpha to beta to gamma. where alpha plus beta plus gamma equals 1. In fact, in practice, it's usually difficult to distinguish the heterozygote, XY, from one of the other two homozygotes. Well, from these proportions, we can calculate the gene frequencies. So if P is the gene frequency of X and Q is the gene frequency of Y, then P will be alpha plus a half beta. The XX only produces X, whereas the XY produces X half of the time. So we get alpha plus a half beta. And similarly, Q will be a half beta plus gamma. And now our population P then can be described by the gene frequencies that it produces. We can write this as an equation that P is little p times X plus little q times Y. Now, let's assume random mating and equal fertility of the genotypes. Then using those assumptions, we can calculate the gene frequencies in the filial population, the first population after mating takes place. And that will be given by p squared. Now that's px plus qy all squared. And remember, we multiply out brackets in the usual way, so that gives us p squared x squared, and x squared is x, so that's the p times x in the first term. We get q squared y squared, and that's q squared y, which is the q times y in the second term. And we get the cross product term twice pq xy, and xy is a half of x plus y. So the 2 and the half cancel, and we get pq times x, which is in the first term, and we get a pq times y, which I've written as qp times y in the second term. Now, of course, p plus q is equal to 1. So that's just px plus qy, which is p. So the gene frequencies remain the same in successive generations under these assumptions. Now, the multiplication can also be used to define a product between genotypes or zygotes. So let's denote XX by A, XY by B, and YY by C. Then we can work out products between the A's, A, B, and C. So, for example, if we want to work out A squared, well, that's XX times XX. That's X squared times X squared. And remember, X squared was just X. So that's X times X. And therefore, A squared is just equal to A. B squared, well, that's XY times XY. And XY is a half of X plus Y. So we just get that term multiplied by itself. Again, remember, we're just removing brackets in the usual way. So we get 1/4 of X times X, X times Y plus Y times X, and YX is the same as XY, so that gives us twice XY, plus YY. And that's 1/4 A plus 1/2 B plus 1/4 C. And what that corresponds to, the B squared there, corresponds to the fact that the mating of 2 B zygotes produces offspring, 1/4 of which are A's, half of which are B's, and 1/4 of which are C's. And similarly, we can work out all of the products between the A, B, and C and produce a little multiplication table such as the one that I've written down there. And here the expression in the row labelled B and the column labelled C is just indicating that B times C is 1/2 of B plus C. Okay, so how is multiplication affected if we allow mutation? So let's consider a similar system with two alleles at an autosomal locus, but suppose also that gene mutation can occur. Well, let pi1 be the probability that gene X mutates into gene Y, and that pi2 is the probability that gene Y mutates into gene X. Then, well, what's the probability that X is produced by the genotype XX? Well, XX always produces an X, so it's just the probability that that X doesn't mutate into a Y. So it's 1 minus pi1. And similarly, the probability that Y is produced by the genotype XX is the probability that the X it does mutate into a Y. So that's pi1. And similarly for the two at the bottom, the probability that X is produced by YY is pi2, and the probability that Y is produced by YY is 1 minus pi2. What about the two in the middle? Well, the probability that X is produced by the genotype XY is, well, XY half of the time produces an X, so we want that not to mutate into a Y, so that's a half times 1 minus pi1, and half the time it produces a Y. And we want that to be multiplied by the probability that that Y does mutate into an X. So we get a half 1 minus pi1 plus a half pi2. And similarly, the probability that Y is produced by the genotype XY is 1/2 of 1 minus pi2 plus a half of pi1. And again, we can summarize that by means of a multiplication. We can write x squared is equal to 1 minus pi1 times x plus pi1 times y. Y squared is pi2x plus 1 minus pi2 times y. And xy is a half of 1 minus pi1 plus pi2 times x plus a half of 1 minus pi2 plus pi1 times y. So those equations are just giving exactly the same information as was in the final box on the previous slide. So next, I want to consider two possible systems of mating and show how we can determine the distribution of types in the nth generation by using the products that we've defined. So let's consider first a simple genetic system again. Let's suppose that we've just got two alleles, X and Y, at an autosomal locus, so it's not sex-linked. We're using simple Mendelian inheritance, and we've got zygotes or genotypes A, B, and C in the usual way. So let's start with a population P, in which the distribution of zygotes is given by that equation. So the proportion of A's, B's, and C's in the population is alpha, beta, and gamma, respectively. And let's assume that mating proceeds by each individual mating with another of the same type, possibly itself, so that the A's only mate with A's, B's with B's, C's with C's. Then what results? Well, the first filial generation, F1, will be given by alpha A squared plus beta B squared plus gamma C squared. Remember, we worked out those products on the previous slide. A squared was A, C squared was C, and B squared was 1/4 A plus 1/2 B plus 1/4 C. Now, if we collect together like terms, the A's, the B's, and the C's, what that we get is alpha plus 1/4 beta times A plus 1/2 beta times B plus gamma plus 1/4 beta times C. What I want you to notice in particular there is that the number of heterozygotes is halved. Okay, so the number of B's is 1/2 of what it was before. Beta becomes 1/2 beta. Okay, so let's suppose that the proportions of A, B, and C in the nth generation are given by alpha n, beta n, and gamma n accordingly. Well, because the B's halve in frequency at each stage, beta n is just 1/2 to the n times beta. Okay, well, write U1 as F1 minus P. Okay, so take the formula that we had for F1 on the previous screen and subtract alpha times A plus beta times B plus gamma times C from it. And what we get is a 1/2 beta multiplied by this bracket, 1/2 A minus B plus 1/2 C. And similarly, if you do the calculation for UN, which is Fn minus Fn minus 1, what you get is 1/2 to the n times beta multiplied by this same factor, 1/2 A minus B plus 1/2 C. Now, if we add the UIs together, notice that the second term of one of the UIs cancels with the first term of the next UI. So we're just left with Fn minus P, and that's the sum of U1 up to UN. And that latter sum is just a simple geometric series. So that when we do that calculation, what we get is that Fn is equal to P, that's the alpha A plus beta B plus gamma C, plus the sum of the UIs, the sum of that geometric series, which is 1 minus 1/2 to the n times beta, multiplied by this factor 1/2 A minus B plus 1/2 C. So what happens in the long term? If we let n tend to infinity, well, the 1/2 to the n gets smaller and smaller very rapidly, so that it quickly approaches the limiting stable distribution that I've written down there. The 1/2 to the n very quickly approaches 0. And so what we end up with is alpha plus 1/2 beta times A plus gamma plus 1/2 beta times C. So notice particularly that the heterozygotes the Bs gradually die out, and their frequency is distributed equally among the two homozygotes, the A and the B. Okay, well, the second system that I want to look at is so-called assortative mating. In an individual who's heterozygous in respect of a pair of alleles, X and Y, so it has both X and Y, each is capable of exerting its own particular and different influence upon the same character. And it's often found that both alleles exert an effect, and the resultant character is a compromise between the two. However, on superficial examination, it can appear that one of the alleles has produced the total effect to the exclusion of the other. And that one is said to be dominant, and the other one is said to be recessive. And if we're only interested in the character produced, we speak of the phenotype of the individual. So let's suppose that we have our same population again, with the distribution of A, B, and C being alpha, beta, and gamma again. And let's assume that the X is dominant. Then we can write that in terms of phenotypes as P is alpha plus beta times D plus gamma times C, where D is alpha A plus beta B divided by alpha plus beta, and that's the genotype distribution of the dominance. So let's assume that we have a situation where, again, we have simple Mendelian inheritance, so Mendel's laws are satisfied, but mating only takes place between individuals of the same phenotype. So dominants mate with dominants and recessives with recessives. Then we can work out the nth generation again. F1 will be alpha plus beta times D squared plus gamma times C squared. And if we do the same calculation as we did on the previous slide, again we get that F1 minus P is a multiple of this same term, 1/2 A minus B plus 1/2 C. And again, the nth generation, as n tends to infinity, it approaches the stable distribution of alpha plus 1/2 beta times A plus gamma plus 1/2 beta times C. So we get exactly the same outcome. The heterozygotes ultimately die out. Okay, well, now I need to get a little bit more technical and introduce some concepts for those who haven't met them before. What we've been describing above are examples of algebras over the real numbers. So let me just quickly recall what an algebra is. It's a vector space over a field which is endowed with a bilinear multiplication. So you can multiply vectors. In simple terms, then, it's a set of objects called vectors, V, and a set of numbers, F, where we can add vectors, we can multiply vectors by a real number, and we can also multiply vectors together, and in each case, the result is another vector. And the elements of the field, the real numbers, are usually called scalars. And there is a set of axioms which simply say that these behave in a natural way. And In such an algebra, there's always a set of vectors, E1 up to En. In this case, I've written it as a finite set of vectors, but it might be infinite, called a basis, such that every vector in the algebra can be written uniquely as a linear combination of the basis vectors. So we can always write it as lambda 1 times E1 plus up to lambda n times En, where the lambdas are just real numbers and the lambdas are uniquely determined. Okay, so in some cases above it was the individual alleles, and in others it was the genotypes, which were treated as the basis elements of the algebra. So in the first case, the x and the y were the basis vectors for the algebra. The typical element of the algebra was a linear combination of those two, the x and the y. In the other case, it was the genotypes, so the basis vectors were A, B, and C, and a typical element of the algebra was alpha times A plus beta times B plus gamma times C. And because of bilinearity, it's sufficient to specify the multiplication on the basis elements. Okay, all I did was I told you what x times y was, or how to multiply the A, B, and C, and that then tells you how to multiply out any elements in the algebra just by removing brackets in the usual way. Okay, well, if A is an algebra, then a subspace, B of A, is a subalgebra if it's closed under the multiplication. So if you add two elements of B, multiply an element of B by a real number, multiply two elements of B, you stay within B. And it's easy to show that the intersection of subalgebras is a subalgebra. So given any subset of A, there's always a smallest subalgebra of A containing S. Simply take the intersection of all of the subalgebras that contain S. And we call this the subalgebra generated by S. An ideal of A is a slightly stronger concept. It's a subalgebra, but not only if we multiply two elements of I together do we stay in I, but if we multiply any element of I by any element of the algebra on either side, then we get another element of I. And just three more terms. An algebra is commutative if xy equals yx for all x and y in A. And remember, because we were dealing with an autosomal locus, the algebras that we were looking at before were commutative algebras. It's flexible if x times yx is xy times x for all xy in A. That's a slightly more general term. Clearly, if the algebra is commutative, then it is flexible, but the converse is false in general. And it's power associative if the subalgebra generated by a single element is associative. So you can define powers of an element, an x to the n, uniquely. It doesn't matter how you bracket that product, you get the same answer. Okay, well, what I want to do next is to speak about evolution algebras. So far, I've been describing algebras corresponding to Mendelian genetics. Evolution algebras correspond to non-Mendelian genetics. And they're motivated both by genetics and by Markov chains in statistics. They mimic the self-reproduction of alleles in non-Mendelian genetics. So when we consider asexual inheritance, that doesn't involve the fusion of gametes, the interpretation of AI times AJ as a zygote doesn't make sense biologically unless AI is equal to AJ. But AI times AI equals AI squared can still be interpreted as self-replication. So evolution algebra theory models non-Mendelian inheritance phenomena. For example, certain bacterial species, because their reproduction is asexual. In particular, evolution algebras model population genetics, which is the study of the frequency and interaction of alleles and genes in populations. Of organelles, which are specialized subunits within a cell that have a specific function, as well as organisms such as potato blight, or the organism that causes potato blight or late blight, which also infects tomatoes and other members of that same family. Okay, so let me tell you what an evolution algebra is. So let A be a vector space over a field F with a basis E1, E2, and so on. Could be finite, it could be infinite. And multiplication given by EI times EJ is 0 if I is different from J, and EI times EI is a sum sigma lambda IK EK. Then A is called an evolution algebra, and that particular basis is said to be a natural basis. Of course, if you were to choose a different basis for the same evolution algebra, it wouldn't necessarily satisfy those same product conditions. So in the rule for EI, you can think of the lambda IK as being the probability that EI becomes EK in the next generation. So that sum is just the superposition of the possible states that can occur when EI mates with itself. And the natural basis plays a privileged role among all other bases because the vectors EI then represent alleles. Okay, some simple properties of evolution algebras. We say that, first of all, that a subalgebra B of an evolution algebra A with a natural basis E1 up to En is an evolution subalgebra if it's spanned by a subset of that natural basis. Okay, well, not every subalgebra of an evolution algebra will be of that kind. It won't necessarily be an evolution subalgebra. However, every evolution subalgebra has the stronger condition that it's actually an ideal. And some properties are that evolution subalgebras are commutative, and that's clear from the way that I've defined the product, and hence it's flexible. They're not power associative, so it does matter how you bracket powers of a single element, you can't define x to the n in a unique way. Depends how you bracket those x's. And evolution subalgebras of an evolution algebra are themselves evolution algebras. And things like direct products, direct sums of evolution algebras are evolution algebras as well. Okay, well, when we study any abstract algebraic system, of fundamental importance are the simple subsystems of that system. And what we try to do is work out what they look like and then see how they fit together to tell us about the structure of the whole system itself. An evolution algebra is said to be indecomposable if you can't write it as a direct sum of evolution subalgebras. Okay, so you can't write it as a direct sum of evolution subalgebras. It's evolutionary simple if it doesn't have any proper evolution subalgebra. Then, thinking about this biologically, a decomposition of an evolution algebra can be seen biologically as a disjoint union of families of genotypes, and each of these families reproduce only with single individuals of the proper family, not with individuals from one of the other components. Now, a generator of an evolution algebra, A, or a basis element, is algebraically persistent if the subalgebra that it generates, so the set of all powers of that generator, is evolutionary simple. And otherwise, it's said to be algebraically transient. And then we have a result which says that if A is an indecomposable evolution algebra, then it's evolutionary simple if and only if it has no algebraically transient generator. And there's a second part. If A has no algebraically transient generator, then it can be written as a direct sum of evolution subalgebras. Of course, that direct sum may have only one element in it, namely A itself. So if A is evolutionary simple, there's only one term in that direct sum. Okay, so let me finish off by talking about the connection between evolution algebras and Markov chains. So Markov chains are stochastic processes for which the description of the present state fully captures all the information that could influence the future evolution of the process. So if you know what the present state's like, you can predict what the future state will look like. And these occur in all sorts of situations, predicting traffic flows, communications networks, genetic issues, and queues are examples where Markov chains can be used to model performance. Devising a physical model for these chaotic systems would be impossibly complicated, but doing so using Markov chains is quite simple. So modeling the to and fro communications traffic over the internet is a prime example of what Markov chains can do. Nowadays, of course, the internet's become extremely complex and traffic moves in a random way between network nodes. Markov chains are commonly used to describe not only the traffic, which is inherently unpredictable, but also how the network will perform, despite the complexity of its structure. And the page rank of a web page, as used by Google, is defined by a Markov chain. Okay, so let me give you the formal definition. A discrete time stochastic process, X, which is a set of discrete random variables, xk, defined on, in my case, a finite state space, lambda, which is the set 1 up to n, then it's a Markov chain if the Markov property holds. That is, if the probability that xk is equal to ik, given that x0 was I0, and so on up to xk minus 1 is ik minus 1, that's exactly the same as the probability that xk is equal to ik, given that xk minus 1 is equal to ik minus 1. So all you need to know is the current situation in order to work out the future situation. Okay, well, a discrete time Markov chain, moreover, is homogeneous if the transition probabilities don't depend on time. And here I'm denoting time by k. So the probability that xk is equal to ik, given that xk minus 1 is ik minus 1, is exactly the same as the probability that xk plus r is ik, given that xk plus r minus 1 is ik minus 1, for every r equals 0 to 1. Then let me show you the connection then. That is that the transition probabilities Pij, the probability that xk equals j, given that xk minus 1 is I, are invariant. They don't depend on the time k. So let A be a finite dimensional real evolution algebra with a natural basis E1 up to En. Then A is a Markov evolution algebra if, in addition, the structure constants satisfy their probabilities, that lambda ik lies between 0 and 1, and that the sum of the lambda ik's is equal to 1. And then the theorem, which is due to Tian, says that for each homogeneous Markov chain X, there is an evolution algebra Mx, whose structure constants are transitional probabilities and whose generator set is the state space of the Markov chain. So if you want to know a little more about any of these structures, then put up a bibliography there. The first half of the talk really is based on very old work of Etherington back in 1941, who first set up the symbolism of genetics in terms of non-associative algebras. Vots Bouzkros in 1980 wrote a set of lecture notes about algebras in genetics. There's been a more up-to-date book by Ljubich called Mathematical Structures in Population Genetics, written in 1992, And then for evolution algebras and their applications, there are lecture notes in Springer by Tian in 2008. Okay, so thank you for your attention.
Okay, thank you, David, very much for your nice talk. I don't know, Fiorella, there are any questions, comments for the public? No question. I have a small question, David. Did you calculate, for example, when you consider X and Y as a basis for an algebra, some structure like Lie algebra or some like that?
No, these are an entirely different class of non-associative algebras. It's very, very unusual for any of the algebras that occur in genetics to be Lie algebras. There are some connections with axial algebras. There are certain algebras that occur in genetics called Bernstein algebras, which I've been interested in, and some of the work on those leads to results in axial algebras. But no, I mean, these algebras, they're not power associative. They don't satisfy x squared equals 0, for example.
Okay.
So,
Okay.
the algebras, they're not going to be Jordan algebras or associative algebras either, because they're power associative. So they don't fit into any of the other natural classes of that we know a lot about. They are quite tricky to study because of that too.
And can one calculate, for example, the Fratini subalgebra and evolution algebra? Do you know?
Yes, there's no reason why you shouldn't do that. You would have to decide whether or not you were going to take the intersection of the maximal subalgebras or the maximal evolution subalgebras. So you would have two different objects there.
Okay.
But yes, it would be of some interest to find out what that looked like. So many of the questions that we ask in these other classes of non-associative algebras, you can ask also but you don't have the usual techniques. In associative algebras, idempotents are important, and of course there aren't any idempotents here. In Lie algebras, of course, you decompose the Lie algebra in again a different way that you couldn't use easily in this context.
Okay. Thank you very much, David, for this conference. Okay, Fiorella, please have you to finish.
Thank you very much, Mr. Towers, for this special conference and for all the special guests for their special participation, and of course all the attendees for joining us in this session of Cátedra Europa. We invite you to continue supporting the education of talented students through our scholarship fundraising campaign, Más Becas, by clicking on the donations button on the homepage of Cátedra Europa. We also encourage you to stay connected to the rest of Cátedra Europa's events. Have a nice day.